So, doing this quick practice, guys, your quiz tomorrow. Your quiz tomorrow will be similar to this practice for the nomenclature part. All right, Sarah, can you take your AirPod out, please? Thank you. Okay, but remember, there's also going to be a few questions from your Venn diagram. So things like acids produce hydrogen ions in water. Acids have a pH range of 0 to 6. They turn litmus paper red. They turn phenolphthalein clear. They taste sour. They react with metals to form hydrogen gas in a salt. And also you can make acid rain from water reacting with one of those non-metal oxides. Right? Or bases, they produce hydroxide ions in water, pH range of 8 to 14. They turn litmus paper blue. They turn phenolphthalein bright pink, BBB. They taste bitter. They feel slippery. If you were asked, Mrs. Tate, how does water feel? It just feels like water, like any other liquid. It doesn't have a special feel to it. They're both electrolytes. They're both corrosive. Neutral things have a pH of 7. In that neutralization reaction, acid plus base yields salt plus water. So that's going to kind of be open-ended, fill-in-the-blank kind of answers for your quiz tomorrow. And then the rest of it is going to be this nomenclature stuff. So what I'd like to do here is kind of go through how I would have approached this if this was my quiz tomorrow. First thing I would have done is I would have scanned for the exception. I know the exception is ammonia. I don't see the word ammonia here. I know the formula for ammonia is NH3. I don't see NH3. So no exception on here. But if it was, what kind of thing is ammonia NH3? It is a base. Get that out of the way. Find it. Make sure you don't miss it. All right, then I'm going to go through and I'm going to label my acids, bases, and salts. I'm going to start with my acids because I know all of my acids will begin with hydrogen. So that's going to be number 1, 3, 5. And then, guys, in the names, every acid will have what in its name? The word acid. I've had somebody call that a salt before. Guys, it said nitric acid. It's an acid. Okay. The bases. You'll know the bases because they end with OH. So I see that here with number 6. And then what would be in the name then? Hydroxide would be at the end. I don't see any hydroxides, which means everything else on here is a salt because we already checked for the exception. So those are all salts. All right, and so then I can go through and start grouping these. We'll do all of our names first. The bases are the easiest because you just name the cation and the anion is always hydroxide. So it just meant Ra. We might have had to hunt for it. It was at the bottom of group 2, but that would have been radium hydroxide. All right, then I would have gone to my salts because those are usually the next easiest. Name the cation, name the anion, but if the anion is an element, make that element name end with IDE. So looking here at number 2, oh, that's easy because there's only 2 elements. So I have to name this calcium, but since that's oxygen, we're going to change it to oxide. Calcium oxide, done. And then for this salt, again, I was nice here. I only gave you salts with 2 elements. So the 2 elements are the 2 ions. K is potassium. And then S I should write sulfide. Change sulfur to ide. Sulfide. So those would be your salts, and then the acids. Those are the tricky ones. Of my 3 acids, the first distinction I need to make is does it have a polyatomic ion or not? These ones had polyatomic ions. This one didn't. So for the one that does not, we can name it immediately. Do I use the prefix hydro, yes or no? Yes. For the binary ones with no polyatomic ions, use hydro. What is the ending that I need to make my name have? Ic, right? This one's still going to have ic, so that's why fluorine is going to change to fluoric. And then every acid we need to write the word acid, hydrofluoric acid. So that was for the one that didn't have a polyatomic ion. For the ones that do have polyatomic ions, we need to know if that polyatomic ion was an 8 or an ite. So for my PO4, PO4 is phosphate. Guys, the O4s are always 8s, O2s are always ites. It's the 3s that you got to think a little more about. So this is phosphate. And if it's phosphate, what did we change the ending to for the 8s? 8s changed to ic. And then here, SO3. Is that an 8 or an ite? That one's an ite. The 3s you got to kind of remember. Oh, SO4 was 8. SO3 is ite. So this is sulfite, and ites change to OUS. And then what about hydro? Do I use hydro for these? No hydro, right, on your polyatomic ion acids. So that means we did have some spelling here because I picked these ones specifically. I'm not going to just say phosphoric acid. What was the root we have to use? Phosphor, PHOS, is the root. And then we can put the ic, phosphoric acid. And then for sulfite, I'm not just going to say sulfus. My root is sulfur is the whole root. And then I can put the OUS acid, pronounced sulfurous acid. So that was the naming side. Then for the formula side, guys, it's all about crisscross. For the salts, that's the easiest because they give you the two ions that you need to crisscross. Let's do a quick review, make sure. We did that the other day, that we know group 1 is +1, group 2 +3, group 2 +2, group 13 +3, 14 +4, 15 -3, 16 -2, 17 -1, 18 doesn't have charges. Okay, so from that, I know magnesium is +2 because it's in group 2. Sodium +1 because it's in group 1. Bromide -1 because it's in group 17. And then I just need to check because I know I've got polyatomic ions. If this is sulfide, are we doing element or polyatomic ion here? Ide is the element. 8 and ite are the polyatomic ions. So sulfide -2 because it's in group 16. Which means when I do my crisscross, this 2 from the magnesium is going to go after my bromide, and that's how I get MgBr2. And then this 2 from the sulfide is going to go after the sodium. That's how I get Na2S. Because 1 and 2s don't simplify. All right, the harder one, though, is the acid. I need to figure out my acid here for nitric acid. Guys, when I'm doing crisscross with an acid, you're always crisscrossing hydrogen with something else. And if this is nitric acid, I just need to decide if it's the nitrogen element, if it's the nitrate ion or the nitrite ion. So first thing I can think about, guys, the fact that there's no hydro here, which one can I rule out? If there's no hydro, it can't be which one? N, NO3, or NO2? Can't be N. And guys, if a hydro was there, it would have to be N. Hydro tells you if it's the element or not. Okay. All right, so then I know it's one of my polyatomics. Now I have to look at my endings, and we had just said if the ending is ic, which polyatomic ion was that? 8, right, Manny? Okay. So that means we're not using the nitrite, we're using the nitrate. And guys, that's then what you're doing crisscross with. Hydrogen +1, nitrate -1, the ones cancel. So HNO3 is your formula. So guys, that's your naming nomenclature part of your quiz. Very similar to that. No more than 10 questions, I don't think. Shock, but we'll ballpark at 10. All right, so last questions, because you'll come in, we'll take our quiz tomorrow morning. Awesome. All right, so then with that, we need to move to that reaction worksheet. Definitely I made comments. A number of you are leaving off charges on ions. Some of you are doing weird balancing things where you're writing coefficients for products, but nothing on the reactant side. And then I'll point out a thing on the neutralization section when we get there. So here we go. Let's get a minute on each section. Make sure, guys, everything should be identical. The only thing that could possibly happen is if you flip-flop your products. But the actual formulas, coefficients, and charges would never be different. So here we go. Here's 1 through 7 on the board. And by the way, acetate can be written in either format. That's why I wrote it both ways for number 7. So some people putting coefficients up here. There will never be a coefficient in front of your acid in these equations. So it's the subscript of the hydrogen that helps you know other coefficients. Questions right now on the ionization section. A lot of students left off charges on those anions. Make sure you got to put those. All right, moving to the dissociation equations. These generally were a little better. Few students, especially ones who weren't here yesterday, are still off on their subscripts. Only polyatomic ion subscripts go to the other side, and nitrate was the only polyatomic ion in that section that had a subscript. Yeah, there's hydroxides, but that doesn't have a subscript. Questions on the dissociation equations? Okay. All right, so let's talk about the neutralization ones. This is just something, when we write the salt, we have to crisscross. And so yes, I oftentimes will write +1, -1 up here, but that is not part of my answer. That is simply work that is not required. Right? But for some of you guys, you're doing this and you're writing your charges where it looks like it's actually part of the formula, which is not correct. You do not write charges in formulas for salts and neutral compounds. So that's something I picked up on earlier in the day, and I actually 4th and 8th period said a little bit more about that, even to the fact where I even suggested if you wanted, you could just write your charges off in the side to be like, okay, 1 and 1, that's okay. Okay, this is +1, -2. All right, I'm going to cross the 2 over. You don't even have to write your charges directly above those because there wasn't a ton of room. But the point is, these guys, no charges because they're not ions. They are neutral compounds. All right, other than that, again, acetate, the worksheet had it in the long form, but it's also acceptable in the shortened form. And I have zero preference about how you write water, H2O or HOH. I mixed it up there on purpose, and I've seen it both ways on semester exams. Back when we got to look at semester exams. You don't look at them anymore. All right, but so you should be comfortable with each. But also I saw some funny subscripts here. Guys, water is water, H2O or HOH. You can't change any other subscripts in water. Question. Go ahead. Again, make sure with balancing, some people had coefficients over here, but not over there, which seemed a bit strange to me. Go. So when you write a HOH, the H gets to balance with the hydrogen and the acid, and then the OH gets to balance with the hydroxide and the base. That's the benefit to writing it is HOH. Is that if you thought about making your list, H would balance with the acid, OH would balance with the base.
Okay, so treat them separately.
So treat them separately for balancing. That's the benefit to writing it that way. I mean, if you would rather just use H2O, and if any way you balance is fine. I'm not grading your process of balancing, just as long as it gets balanced. Okay. All right, other questions here? Okay. This is not on your quiz tomorrow. But you're not going to see it again until your test review and then your test. So some of you might want to take some time, if you have it, to go back over this, make sure you feel good, review the video. All right, then with that, we need a blank sheet of paper for number 56, acid-base definitions. We're learning the rest of our definitions for an acid and a base today, and then we're going to apply one of those new definitions. Okay? Acid-base definitions. FYI, I've seen it more the past few weeks. Guys, the year's not over yet. I suggest perhaps picking up a pack of paper if you're getting low. We still have more notes to take. Take the pass. Okay. So, we have 3 different definitions of an acid and a base defined by 3 different scientists. And guys, we can do this because there's nothing, it's not based on the type of bond. Remember I said that an acid could have an ionic bond or a covalent bond. It's really all about their behavior. And so we have found that applying these different definitions, they still meet some of our basic requirements for what makes something an acid, like the pH would be between 0 and 6. But it's just trying to get better at how we think of what an acid and a base actually is. So I will say, as we go down this list here from Arrhenius to Bronsted-Lowry down to Lewis, that the definitions do become bigger and bigger, meaning more and more compounds would meet these definitions. It means that we can call more things an acid and a base than if we only stuck with Arrhenius's definitions. So, as you guys are filling this in, Arrhenius is the review one because I wanted them all in one place. He's the what did it make in water guy. Arrhenius says an acid makes H plus hydrogen ions in water, and he says bases make hydroxide, OH minus in water. So those are your Arrhenius definitions of an acid and a base. That's what could be on your quiz tomorrow. But then we move to the Bronsted-Lowry. 2 different scientists, Bronsted and Lowry, they both get credit here. And the Bronsted-Lowry definitions of an acid and a base focus entirely on the hydrogen ion. So I'd mentioned to you guys yesterday when we were talking about our ionization. You guys remember I said a hydrogen ion was the same thing as a proton. Got 80 baby protons, so tiny. Right? And I just want to reiterate that real quick. You're not going to draw this in your notes, but if you were thinking of an atom of hydrogen, an atom of hydrogen has 1 proton in its nucleus, has no neutrons. The most abundant isotope of hydrogen has no neutrons, and then it only has 1 valence electron. And when we make it an ion, an H plus ion, we take that electron away. And so that's what I was trying to show there, that it's just a proton. And so you guys should start becoming more comfortable in chemistry. We go back and forth between saying proton and hydrogen ion all the time. There's no single more common way that people talk about this. So Bronsted-Lowry, they view acids and bases as actually moving protons or hydrogen ions between them. So an acid is a proton donor. A base is a proton acceptor. And guess what? Bronsted-Lowry said an acid would give its proton to the base. They think of it as a proton transfer. And we're actually going to label this in equations showing the proton transfer of the hydrogen ion from the acid to the base. So, guys, this doesn't change a whole lot for the acids, because if Arrhenius says you got to make an H plus in water and Bronsted-Lowry says you got to donate an H plus, guess what? Every acid is still going to have hydrogen in its formula. It's still going to start with H. But where the big shift comes, guys, over here. Now, to be a Bronsted-Lowry base, you do not have to have hydroxide. And so, for your quiz tomorrow, the exception, ammonia, NH3, it is a Bronsted-Lowry base. It doesn't have hydroxide, but it is great at accepting protons. Right? So that is the Bronsted-Lowry definition. We're going to hang out here for the rest of class after we do our 3rd definition using that one in more cases. All right, so the last one on here is Lewis. I always remember this because isn't Lewis the Lewis dot electrons, Lewis dot structures, Lewis dot diagrams? Lewis was the dot guy, and all of the dots were representing what? Electrons. He's the electron guy. And oh, look, his definition is about electrons. Ha ha. Shocking. So he's going to view acid and base behavior as transferring electrons. But now it's going to go in the opposite direction. The base is the electron pair donor. The acid is the electron pair acceptor. And there is a transfer of one to the other. The base donates its electron pair to the other, which means now, guess what? You don't even need to have hydrogens anymore. That's a pretty big definition. We don't even get into a lot of that in AP chemistry. It's more complicated. But we should be aware that the definition exists. So, if you had like a matching section on a test or something, right? First job is just getting the right person with the right thing. So that's why I said Arrhenius is the what does it make in water guy, which ion does it make. Bronsted-Lowry is about the proton transfer. Lewis is about the electron. And then you have to remember, especially for the transfers, which way it's going. So we're going to spend more time here. That's the one that I hope you get really comfortable with. An acid is a proton donor, a base is a proton acceptor. Because guys, Lewis is always the opposite direction. And I remember that because electrons have the opposite charge of a proton. So if the positive thing is going from the acid to the base, then the negative thing is going from the base to the acid. So that's how I kind of keep those straight, is I know my Lewis definition because I compare it to my Bronsted-Lowry. If the acid is the proton donor, it's got to be the electron pair acceptor. Right? They aren't both donors or both acceptors. It's the opposite for those different definitions. Okay, so this leads us to another vocabulary word. Somebody had brought this up in one of my classes, that they were asking about water and HOH and whether you would call it an acid or a base, because you're like, Mrs. Tate, it starts with an H, it ends with an OH. What is it? It's actually a special group of compounds called amphoteric. And amphoteric, if you think of that prefix AMPH, similar to amphibian, and not quite the same, but similar to ambidextrous, meaning both. Amphibians live on both land and water, right? Ambidextrous, you have both hands are dominant. If you're amphoteric, guess what? That proton, it can go both ways. You can donate it, you can accept it, you could be an acid or a base. Right? So amphoteric, a substance that can act as either an acid or a base. It just depends on who's around it. That's what's going to make the decision to whether or not it's acting as an acid or a base. It's who's near it, who's around it, what's going to happen. So, let off with this. The most common example of an amphoteric substance is water. Water can accept a hydrogen ion. Water can donate a hydrogen ion. But another example is the hydrogen carbonate ion. That's one that you did memorize. It's not showing up on your quiz tomorrow. Don't panic. But HCO3 minus is hydrogen carbonate. NaHCO3 is baking soda. So baking soda has this ion. If I dissolve some baking soda in water, it'll make this ion, and this ion is amphoteric because it can pick up a hydrogen, right, which means it would be a base acting as a proton acceptor, or it can donate a hydrogen, meaning it would be acting as an acid. So those are some examples of amphoteric substances. All right, so we're coming back to this Bronsted-Lowry definition, and we're going to start talking about these concepts called conjugate acid-base pairs and kind of labeling what's actually going on in different equations. So a conjugate acid-base pair is going to be two different substances, because it is a pair, and the chemical formulas for those two different substances, they differ by only one single hydrogen ion. So on a test, you could be asked, hey, identify, which of the following is a conjugate acid-base pair. And all you're going to do is you're going to look at their chemical formulas, and the only thing that can be different between the two chemical formulas is one hydrogen ion. So giving you some examples of that. NH3, NH4 plus. You see how the only difference is one hydrogen ion? They both have a single nitrogen, but we have 3 hydrogens versus 4 hydrogens. That's a conjugate acid-base pair. We could also do Water and hydronium. They both have one oxygen. One has 2 hydrogens, the other has 3. We could also do water and hydroxide, because they still both have one oxygen, but now we have 2 hydrogens versus 1 hydrogen. They only differ by a single hydrogen. So don't write this one down because I'm going to erase it, but oftentimes they put as a wrong answer choice on a multiple choice question where they will put H3O plus and OH minus. Why are they not a conjugate acid-base pair? What do you got? It's 2 hydrogens. Not okay, guys. Cannot differ by 2 hydrogen ions. Only 1. So why is that? The idea is that these guys can turn into each other. They can turn into each other after a proton transfer. So the idea is if NH3 accepts a proton, what would it turn into? Oh, it would turn into NH4. If NH4 donated a proton, what would it turn into? Oh, it would turn into NH3. They can turn into each other. That's what makes them a conjugate acid-base pair, and that's why they can only differ by 1 hydrogen ion. It's an acid-base pair because you can label within the pair, one of them would be acting as an acid and one of them would be acting as a base. We're going to write this in our next section too, but the idea is within a pair, the acid would always be the one with the extra hydrogen. So if we have 3 hydrogens and 4 hydrogens, guess what? In this pair, NH4 plus is the acid half of the pair, which makes NH3 the basic half of the pair, the base, because it is an acid-base pair. And so that's why I say as an acid, if this donated its hydrogen, then wouldn't it turn into NH3? And then now NH3 it could accept a hydrogen, and then it would turn into the acid, and then the acid could donate the hydrogen, and then it would turn into the base. Like they can go back and forth. So I could do the same thing over here. I could say, oh, H3O plus is the acid because it has 3 hydrogens, but water's the base because it only has 2. Right? But then look at the other example. In this case, wouldn't I say water is the acid because it has 2 hydrogens, and then OH is the base because it only has 1? Oh, look, acid, water can be an acid or a base. It's amphoteric. Right? Just depends on who it's with. Okay, so let's take this and let's now get to actual equations. We like to write equations that are showing reactions with acids and bases involving these proton transfers. And these are going to involve formulas that are not necessarily like always start with H, always end with OH, because we're using the Bronsted-Lowry definition. So what I'm going through here is I'm going through my steps, right? Just like I was doing with the reaction, step 1, step 2, step 3, even though I know it's labeled A, B, C, D. So what are we going to do first? You're going to have an equation, and it's going to have 4 different formulas in it. The first thing that you're going to do is you are going to identify the conjugate acid-base pairs in the equation. So you're going to look at those 4 chemical formulas. And 2 of the formulas, the only difference between them will be 1 hydrogen ion. And then the other 2 formulas, guess what? The difference between them will only be 1 hydrogen ion. So if there are 4 formulas total, you will have 2 pairs. So that's step 1, find the pairs. Step 2, you're going to label the pairs. Just like we did here, you're going to label within each pair which one is the acid half of the pair and which one is the base. So we're going to label the acid and base within each pair. Label the acid and the base within each pair. So this is where we're going to write it. How did I know up here which one was the acid? What did I look for? The one that had more hydrogens. The acid has more hydrogens than the base. The acid has more hydrogens than the base. Okay, so at this point, I've now labeled all 4 of my formulas as either an acid or a base. But that can be confusing because that means we'll have 2 acids and 2 bases. So my step 3 is just a vocabulary trying to clean it up so that there's no confusion if I say what's the acid, which one am I talking about. What we're going to do is we're going to add the word conjugate to the product labels. The labels that you gave the products of acid and base, you're going to add the word conjugate to the front of it. And again, that's just on the product side. So, number 1, why we do that? Because that now means that you will not have 2 things labeled as an acid. You'll have 1 thing labeled as an acid, and you'll have another one labeled as a conjugate acid. And so that makes it very clear on a multiple choice question if I say, or not, which one is the acid or which one is the conjugate acid. Now you'll know the difference between the 2. Why do we put it on the product side? This word conjugate kind of makes me think of like a magician that's going to conjure up something out of thin air, right? They're going to make something. That's what this word means, conjugate. It's what gets made. And in a chemical reaction, don't the products get made from the reactants? So that's what we're saying, is we're saying the conjugate acid, that's what's got made in this reaction. The conjugate base got made in the reaction. We didn't start with it, we made it. All right, last thing that we'll do here is going to be about the arrows. You're going to draw arrows showing the proton transfer. And so I'm just going to put on here how the arrows are going to look. You're going to go to your equation and you're going to find what you've labeled the acid. You're going to find what you've labeled the base. And the arrow always goes acid to base. The acid donates the proton to the base. But you're also going to do it where it has your conjugate acid and your conjugate base. Conjugate acid, conjugate base, acid to base. The arrow always points acid to base or conjugate acid to conjugate base. You should never mix up though and like draw an arrow from a conjugate acid to just a base. It's like the conjugates stay together and the non-conjugates stay together. You put H+ here. All right, so those are the steps. So with that, we're going to go to our worksheet now, where I'm going to do an example directly on the worksheet, and then we're going to add one more set of notes here. So we're going back to 55. And so, by the way, this is the back only, because we've already done the front, which is going to be due tomorrow, Thursday, 8:25 a.m. And here we go. I'm doing that example at the top. Okay. All right, so if we look at our instructions, we are going to label the Bronsted-Lowry acids, bases, conjugate acid, conjugate base, and then we're going to show the direction of the proton transfer on both the product and the reactant side. This is what all my steps take us through. So here we go, step 1. Step 1 is identify the conjugate acid-base pairs. So in this equation here, I'm just going to start with the HCl, and then I'm going to ask myself, between these 3 formulas, OH minus, Cl minus, H2O, which one is different from the HCl by only 1 hydrogen ion? First, second, or third? Okay. I said first, second, third for my checks. Second. I think you guys are saying third one overall, but it was the second one with my checks. Guys, this one, it can't be this one because that's got an oxygen and this has a chlorine. That's differing by more than 1 hydrogen. Here, this has an oxygen, that has a chlorine, differing by more than 1 hydrogen. But oh, look, this has 0 hydrogens, that has 1 hydrogen, they both have 1 chlorine. That differs by 1 hydrogen only, which means that's my first pair. What we often do is we draw a bracket. You'll see this in every textbook also, kind of linking those. What this tells me is that the HCl turned into the Cl minus after a proton transfer. Now, still in step 1, the other 2 formulas. Guys, they should be your other pair, but let's just double check. Is the difference between OH minus and H2O only one hydrogen ion? Yes, right? They both have one oxygen and then one hydrogen versus two. So there's my other pair. I draw another bracket. Mrs. Tate, is it always the first go together and then the seconds go together? No, sometimes it's the outsides and the insides. You've got to look at the formulas. So that was step one, identify the pairs. Step two, you need to add labels. And for your labels, we said that the acid is the one that had what? More hydrogen. So I'm focusing just on my blue pair. And in the blue pair, who has more hydrogens? HCl. That means it's the acid half of the pair, and the Cl minus is the base half of the pair. And let's do the same thing for the OH and the H2O. That's my green pair. Who is the acid in that pair? The H2O, because two hydrogens are more than one hydrogen. That was step two, labeling each half of the pair. Mrs. Tate, is it always in that order? Acid, base, base, acid? Nope, depends on the equation. You got to look at the pairs. Step three, add the word conjugate to the labels on the product side. So instead of just calling this the base, we're going to call it the conjugate base. And instead of just calling this the acid, the water, it is the conjugate acid, because those are the things that got made in the reaction. So that was step three. And then finishing up with step four, it's about drawing the arrows. The arrows always go acid to base. The acid is the proton donor, the base is the proton acceptor. And then on the other side, conjugate acid to conjugate base. Mrs. Tate, do the arrows always both point inward? No, sometimes they both point to the right, both to the left, both in, both out. It just depends on how the equation was written. So last thing up here, Mrs. Tate, why do we put the arrow on this side? Well, we don't get into this in honors a lot, but reactions can be reversible. So this is just saying if it was reversible, if I wanted to go back and reform these, that's how the proton would get transferred. Go away. All right, so you have 5 more of those to do on your own, but let me get down here to this last part here. In this table, I've given you 1/2 of a conjugate acid-base pair, and you have to give me the other half. We know the acid should always have an extra hydrogen, right? The base should have one less, but I just want to be clear here that if you are filling in the acid half of the pair, yes, you are going to add a hydrogen to the formula. If it's not there, put it there. But you also have to add 1 to the charge, because it's a hydrogen ion with a positive charge. So if I'm looking at this one that was already done, if I said, oh, I was given the base and I need to fill in the acid, we went from H to H2, but notice the charge went from -1 up to 0, which is neutral, right? Increase the hydrogen and increase the charge. Conversely, if you needed to do the base, you would take a hydrogen away. If there's only 1, take it all away. But then you also need to subtract 1 from the charge. And so again, looking back at that example, if I were starting with the acid, I would have said, okay, take an H away, go from H2 to H, and then this charge was neutral, that's 0, go from 0 down to -1. And so just thinking of a number line, 0 is on this number line, -1, +1, make sure you're not skipping over 0. Okay. So I'll do one more each here. Let's do this one, 29. I was given H3PO4 and I want the base. So first of all, am I on the add or subtract side? I'm subtracting to make the base. So my H3 is going to go to H2. I'm going to leave the PO4 alone, never touch the non-hydrogen things. And then my charge. What was my charge originally? If there's nothing there, it's understood to be 0. And I have to subtract 1 from the charge. So this is going to be negative. 0 down to -1. But doing this one here, this one here, now I have the base, I'm going to the acid, which means we're adding. So I need to add a hydrogen, but there's no hydrogen there. Okay, just put one in. Hydrogens typically go in the front. Leave the F alone, and then my charge, it was a -1, but we're adding 1 to it, which makes it 0, and we don't write zeros, that's just neutral. So that's it for that one. All right, so that's it for the worksheet, just finishing those 2 tables at the bottom and doing these equations. Guys, I will point out that when water is in both locations, it is possible that we might do our brackets differently. So I'll point that out on the answer key tomorrow. As long as you do it correct for your paper, you're fine. And yeah, some students were concerned if they're reversible reactions, how do you know where to put conjugate? Guys, product side is always on the right side. No matter if the reaction is reversible or not, we always call the right side the product side. Okay, questions for me right now? So again, this is just an application of the Bronsted-Lowry definition. While some of these are formulas that look like acids or bases to you already, there are sometimes going to be things on here that are not your typical acid and base formulas that we did for the acid-base salt worksheet. That's what Bronsted-Lowry can do for us. All right, so with that, just this due tomorrow on Canvas and quiz tomorrow. Make sure you're ready to go.